then we define field. We will show after that it is a field, and we define this application. We will show after that it is an absolute value. If we have a class of Cauchy sequence, then is defined to be of all Cauchy sequence such that this sequence is equivalent to, which means that the difference between the two is a convergent sequence, is a sequence that converges to 0. Then in order to prove that is what we need to prove. Then we need to prove that first that K is a field. And for that, it suffices to prove that, we just need to prove that I is a maximal ideal. The second point is to show that the absolute, the map that we define here is an absolute value. And we need to show in the end that this one is complete. And we need to construct in the end a map from K to K8 such that the image K is dense. And I will let the two first one, I will let them as an exercise. If you have any question, I can give you the, if you cannot solve it, I can give you the solution of that. And I will just prove that with respect to this norm, any Cauchy sequence is convergent. I just and before continuing the proof, if we have if, for example, we have is a sequence such that it converges to an element x, then and if for all sequence equivalent to x, and for equivalent to x, we have converge. In particular, we have then the class, the absolute value of the class of x is exactly equal to the absolute value of x, which is not necessarily the case if we take any sequence who converge to x. We need to take this norm to obtain this result. Then this means if we want to construct an embedding from k to k head, we just need for an element x to associate the sequence, the constant sequence, the class of the constant sequence in x. And this class is all the sequences that converge to x. You can see them like that. And from here, this up is an isometry. Then come back just to the that we will prove that the set is dense. And for example, how to prove then just by that, then if we consider any Cauchy sequence Cauchy sequences, then it suffices just to take as xn to be a class of x. And here we have n. This is constant sequence. And obviously by construction, converge to the sequence. Then if we consider sequence xn, then it is a sequence of sequence, which means for each n it is equal to something like that. Refer to Then we will construct and just how we can find the elements. And X will be the sequence defined as below. And such that we just need to find one and it will be equivalent for all the other sequence. Just to see. We fix a representant family of the sequence. Yeah. And we set such that we have this is possible because this sequence is a Cauchy sequence. This sequence is a Cauchy sequence. I will give you the proof of all the statement later in the note. But I will just say that we can prove as an exercise. We have this Cauchy sequence converge to X. Then it's complete. Now, if we suppose that there exists another field for which we have there exists an embedding from K to this field and it is dense, then we will show that it is unique. If we suppose that is another field such that there exists an embedding from an isometric embedding from K to K such that is dense.
老师，同学您好，请在教学楼入口或进入教室后主动扫纸巾码，全程佩戴口罩。
Then we can construct a map from. Then we have the following. And if we have an element here, say X, then there exists a sequence here such that converge X because it is continuous. E is an isometry, hence a continuous map. Then this works perfectly. Then all we need to do is just the image. We will construct a map from here to here called phi, and in that case, phi of X is exactly the limit of I And by construction, we will have the absolute value of x is exactly the same as here. Because this one is an isometry, and from some rank, they are equal. Therefore, isometry. Then we can come back to our first example. Then if we consider Q endowed with such that is a p-adic absolute value, then we have the following. Now the completion of Q we will denote the completion of Q as to be QP. And in that case, you can see this set as follows. It's like a long series and the P. Such that EN one and we will denote the ring of P ZP, and in that case it is exactly all the series which means that P is not invertible in ZP. And the good thing about that, the residual field of QP remain the finite field FP. Z just for the maximum idea, in that case, it will be exactly P ZP and the residual field of QP is ZP ZP, and hopefully it is exactly FQ. Just as a remark, ZP is compact because it is closed. It corresponds exactly to the closed disk, and it is bounded by 1. Generally, on Q, we know all the absolute value that we can define over Q. And if any absolute value not necessarily ultrametric. On Q is equal to one of following first one. It can be the trivial one, but we denote by like that 0, 2. The usual one that we denote like that, and 2 a p-adic absolute value, which means for one p we can define several absolute values. They are, even if they are they define the same topology, but they are different absolute values. And we need to fix R an element between 1 and 0, not equal to 0, not equal to 1, with and the absolute value of P is equal to R. This is necessary. In particular, we will denote by for the specific one. If we have in particular is equal to P minus 1. With this setting, then we can check that P be the set of all prime number, positive prime number. Then for all x in Q, we have the product of all the absolute value is exactly, yes, here just we fix, for each P, we fix the specific absolute value. We don't choose anyone. We don't choose, then it is exactly equal to 1. This is a nice exercise if you want to do it. You just need to use the factorization of any element, of any integer to factorize it into a prime number of any integers, and you can obtain this result. Well, there exists another kind of complete field We give an example here. Then just consider any field with a trivial absolute value. Then the field of long series, that we denote as follows. With this absolute value just means that we consider the first coefficient that it is not the index of the first coefficient that it is not equal to 0, and we take the r power this index, and r is an element r is an element between 0 and 1. It looks like the same as in the p-adic case. They look like similar, but they are not. This is correspond to the p-adic absolute value. And in this case, the ring of you can say that it is the ring of integers of k in somehow, because in that case, it is exactly the ring of power series. And we know that this ring is a local ring, and its maximal ideal is exactly maximally ideal. In that case, it's exactly the ideal generated by T. Just be careful. For example, this field. if we consider, and if in the, for example, if we consider a finite field FP, then even if they looks like the same, they are not isomorphic as an ultrametric field. The now we start a new section that concern normal vector spaces over automatic field. We know this theory when we work with real number or vector space over R. But the question is, there a theory that with normal spaces that over an ultrametric field? The response is yes. Then normal. Over. And we will see that there is many property that we can find for real vector spaces that we can found also for vector spaces over a non-Archimedean field, complete field. It's necessary to use the completeness. Then we will define what is a bounded operator when we are working with ultrametric field, and we will use that after that. For example, when we if we have an ultrametric field, what we can say, if we have an ultrametric field and we have a finite extension of this field, the question how we can extend this absolute value? Is there a way, and if there is a way, it is a unique way to extend an absolute value? Then we start by giving some definition, and we will show after using ultrametric analysis to show how we construct the extension of the absolute value. Then definition. Then we fix, for the moment, we just work with any ultrametric field. We will not assume that the field is complete. It's not necessary for the moment. Then a vector space, K vector space, K norm on V is a map such that, and it satisfies the same property as the usual norm that we are used to use when we are doing real analysis. Then for any vector and it is equivalent to the equal to 0. In the case if there is no equivalence, for example, in the case if we have just this, then we say it is a semi-norm instead of a norm. This is just for, but we will use norm, not semi-norm, only in one case that we will detail later. Then for any, and this is for the compatibility with the absolute value, and for any element k, element in k, and v are vectored, then it looks like the same property as in the complex number, real number. And the last one, since it is we need the triangular inequality, but since k is ultrametric, then the triangular inequality will be probably a strong triangular inequality. Then we just assume that it is directly the strong one. Then when we call this pair, no, or just normal vector space if it is obvious from the context which fails on. Then, as usual, then we defined a morphism between two normal spaces is just a collinear map, but it is bounded. Or we can say it suffices to show that if it is continuous, then it will be probably a bounded map. No, normal space, just normal space. Not. And if first is collinear and it is bounded, which means that there exists a constant c this such that for all v is equivalent to say that it's continuous. If a collinear map is continuous, then we can prove that it is bounded. Continuous with respect to this to the topology induced by the norm over each vector spaces. And we will denote all the set of then this we can define a norm on this vector space that we will call the operator norm. So for any phi, we can define and v is different from 0, which coincide also with all the nth of all the constants that satisfy this inequality. We have the same operator norms is exactly the same as in the real case. We have a specific also a subspace of such space that we will call an if in particular C is equal to 1, then we say that is contracting map. And the set of the subspace which is, we can see it as the closed ball of with center 0 and radius equal to 1 of this K vector space with respect to this norm. Now we can define what we mean if we have two norms. What we mean by equivalent norm. This is the K of. Then we say that they are equivalent if and only if the identity with respect to each norm in other words, we are just saying that as K-normed space, they are isomorphic. Now, as since for any norm we can define a metric, then we have the notion of Cauchy sequences, and as in the real case, we can define the notion of Banach space when we are considering vector spaces over an ultrametric field, and it is exactly the same. And as if we do it before, for any vector spaces, there exists the completion and of this vector space, and the construction of this completion, if you understand how we did it before, then you can do it in an analogous way for vector spaces. We are not doing, we just assume that for any normal spaces, we can construct a Cavanagh spaces that will contain the first one, which is dense for this. Then a Cauchy sequence. Normal space. If I'm same definition for all epsilon positive, there exists such that for all m and n apply less than epsilon. A complete space. Now we just need to define another notion which is necessary for the next section. If we have a normal spaces and we have a subspaces, then if we consider the quotient with this subspaces, then we can define a norm in these spaces in some condition. If initial K vector spaces is complete, then it is the same. Then if the subspace is closed, then it is the same. Then the quotient is also a Banach space. If we consider the normal space. Then in one hand, we can restrict the norm, and it is also a normal space. And we call the residual norm. Then we can observe that it looks like the same as when we defined in the beginning the norm here. This norm. We define this norm is just, in some sense, it is the residual norm induced by this one. this one. This one is the residual norm, induced by this one. Such that is cohomology. And it is well defined as a norm. By construction, it is well defined. Usually it doesn't depend on the representant of each class. And in particular, we can recover the exact sequence, the usual exact sequence, and it is an exact sequence in the category of normal space, which means that we have, if we have V here with this norm, so the residual norm with 0. Projection. This is the projection, and this is bounded. Not only bounded, but it is a contracting map. And this one is done isometry. And it is that. And everything is well defined. Now we think that and the other important point that we should define, then we have the notion of normal space, and we have also the notion of normal algebra. And just need to show something. A K normal algebra with unit. This is important. Then as a K vector space, it is a normal space. Just we need to, this norm need to satisfy more properties than the one for normal spaces, because we need to have the, for example, if we consider the multiplication by an element of A, we need to have the continuity of this R. That's why we impose the following properties. then we need to have the norm of 1 is exactly equal to 1. And for any x and y and a, we have, then this inequality implies the continuity of the multiplication. And we need to be careful. If we consider a K-Banach algebra, K-normed algebra, this doesn't mean in any way that the norm is multiplicative. We just have this one. And we will see it, for example, if we consider the matrix or operator, if we consider the norm operator, like in the real case, the composition of two operators is not the product of the two norms. However, we can resolve this partially, this problem. And in the case of if with respect, if then the most common example, and we will see some example here. An example where the norm is not multiplicative, another one where the norm is multiplicative, and they are too important as an example. Then, for example, if we consider P space, or a Banach space, but generally, if here I didn't say, but if W here is a Banach space, then all this set will be a Banach space. That's why here, if LKP is normed normed algebra, and in the case of if V is a Banach space, then it is the same for this set. In particular, if we, for example, if we consider a finite finite space or we just consider the matrix, the set of matrix. We can define, and it will coincide with the operator norm. Then if we consider the set of matrix on big K, and the norm here will be, if we have a matrix here, we will just consider the maximum of each coefficient, and it will define, in the case of, in the ultrametric case, it will define a norm maximum of, moreover, it will coincide with the operator norm. If over is, and is exactly the same. Then if we fix this norm, on Kn, then the set of matrix we coincide with the set of collinear bounded map on Kn, and it, by fixing a basis, then we can associate a matrix, and the norm here we coincide with the operator norm. Now there exists another type of example. Then if we will assume here that K is complete for the simplicity. Then for any K and R, we can define we will goes A. And for any polynomial, you can write it in this in the following way. Maybe see. And we can define this. Define a multiplicative if the center is 0, then you just say equals 1. Then define multiplicative norm in just A. this norm can extend to the fraction field of this. This is just a notation. Extends to fraction fields, and we will denote just for notation. Here, I'm gonna just the completion with respect to this absolute value. In particular, if we consider a k, a k-Banach algebra, and we endow it with a multiplicative norm, that it is in particular an absolute value if our ring is a field, and if we endow it with a norm, a k norm, and if this norm is multiplicative, then it is in particular an absolute value in this field. This is the completion of that. This is just to have, because we will use it after for p-adic differential equation. For p-adic differential equation, we will not look only to the solution that on a neighborhood of a point of k. We will just we look, for example, to the solution of a neighborhood of a point of this. I will explain it later. This is just, for the moment, this is just a notation. Then, now we can define, as I said before, even if the norm is not multiplicative, but we can find something that can make things more better. For any, then if we have a k algebra and we have a norm, then we can define another map which called the spectral semi-norm. In general, it is neither a norm or a semi-norm, but I will explain why we call it a semi-norm. Then the map, you can defined as follows. This limit exists as a limit, and this limit exists always. There is no problem about that. Spectral. Or we can call it in some book, they call it spectral norm, but it's preferable to put spectral semi-norm, because why I use semi, because we can have some x that are different from 0. They are not nilpotent, and they have the spectral absolute, the spectral norm semi-norm equal to 0. And we call such element quasi-nilpotent elements. Then, as first properties, we have the following. For any x in A, the spectral semi-norm is always less than the norm. The norm is always less than the norm. 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 And obviously, we have the spectral norm of 1 is exactly equal to 1. Then, now I will explain why we call it seminorm. In the case if we have then x and y in A such that x and y commute, then we have the following inequality. Then in particular, if my k-Banach algebra is commutative, then it is defined really a seminorm on this algebra. There is another point that this is a point. Then the good point about the spectrum, and if we have for any element x on A and any natural numbers, positive number, it's important because we not the same. Then we have the spectral norm of x n is exactly we say that in that case we say that it is power multiplicative. And in the case before, if the initial norm on my K algebra is power multiplicative, then we can conclude directly that it is equal to the spectral norm. And this norm, for example, if we consider the matrix that we matrix norm that we considered before, then it will be exactly equal to the maximum of the absolute value of the eigenvalue of this matrix. This notion is really important because after when we want to compute the radius of convergence of the solution of a differential equation, in some case we will use the spectral norm that it is more easy to compute than the radius. And the good thing is if you have two equivalent norms, then the spectral norm of each one, if we have two norm equivalent, then the spectral norm associated to each one, they are equal. If we have then which means that it depends only on the structure of the Carnot space. Now we can announce one of the most important theorem of the p-adic functional analysis. And we suppose that K is complete. Then we have the same result as in the real case. If is a finite with finite dimension, then is a Banach space. And if we consider a finite vector space, any norm defined in this, if we define two norms on this vector space, then there will be probably equivalence. Then this means that any norm defined, all the norm defined on a finite dimensional vector space, they are equivalent. Then we can finish this part concerning this all this definition, and we can go back to the finite extension of an ultrametric complete field. No one. In the beginning, we talk about the closure, the topological closure, which is the completion of the fields. Now we will talk about the algebraic closure and how it behaves, how we can define all the stuff concerning this. Then the first question that we can ask ourselves, if we have, we consider a complete one, because otherwise it's the theory of algebra, which is not necessarily interesting. Be a complete. If question, if L is a finite extension or more generally, if it is an extension, algebraic. And the question, if it's extend to n, and if we can find, and if it is unique, then the next session will be tomorrow at 10 and a quarter, and we will prove how we can construct, how we can extend this absolute value, and in particular this absolute value will be unique. Then we can finish here. Is there any questions?